Hello. In this lesson, we are going to talk about a process in semiconductors called doping. So, doping basically means improving the performance of something. So, for example, in athletes, they take enhancement drugs and they call that process doping, so that their performance in some sports event would be improved. So the same happens for semiconductors. So for example, if we have a pure semiconductor, let's take silicon in this case. So this is a one crystal structure of silicon. So it has 4 valence electrons since it is in group 4. And these 4 valence electrons are covalently bonded to their nearest neighbors. So when we say doping, we are to add impurities addition of impurities to semiconductors such as silicon or germanium. So these impurities can either be can either have 5 valence electrons or 3 valence electrons. So we will take the case first for adding an impurity with 5 valence electrons. So suppose now I remove one atom of silicon in this structure. So this still has its electron for 1, 2, 3, 4. Now I will introduce another atom that has 5 valence electrons. Say I'll introduce, what's the 7? Arsenic. So arsenic in group 5 has 5 valence electrons. So I will put here arsenic. Now, in order for it to bond inside this structure, its 4 valence electrons will bond with the neighboring silicon atoms, and its remaining electron, since it has 5 valence electrons, it still has 1 electron, will be sitting around floating inside this structure. So this is called an N-type semiconductor. So the N meaning negative. So this type of semiconductor will behave differently from the pure semiconductor of silicon or germanium. In this case, its energy band will look like this. So this is the conduction band and this is the valence band. But since we have introduced an impurity such as arsenic, this extra electron inside this structure will be sort of it will require less energy for it to jump into the conduction band. So it introduces another band. So let's say this is the electron from, we can also call that sometimes semi-free, since it is still in the atom but it has nowhere to bond. So it's a free electron from arsenic. So its energy level is very close to the conduction band. So if we apply, for example, an energy to this free electron, we apply an energy to this free electron, it can easily move, or it can easily participate in conduction. So this improves the conductivity of our semiconductors. So this is called the N-type semiconductor. So it's important to note that in this structure, everything is electrically neutral. What we mean by that is no electric field exists in this structure. No net electric field exists in this structure. So silicon has a certain atomic number. It has a certain nuclear charge, and that balances out with its number of electrons. Same goes for arsenic. It has a certain nuclear charge, and it balances out with its number of electrons. So this structure is electrically neutral. So next we have another type of doping. So let's construct again our pure semiconductor. So let's say now this is germanium. So germanium also has 4 valence electrons. And now instead of taking away this one germanium atom and replacing it with 5 valence electrons, let's replace it with an atom in the group 3 with only 3 valence electrons. So for example, we have gallium. So gallium only has 3 valence electrons. So among these 3 valence electrons, they will participate in covalent bonds with their neighboring germanium atoms. Now what happens is there will be a hole inside this structure. So this hole acts as if it's a positive charge, because this positive charge would want to steal electrons from its neighboring atoms. So this positive charge actually wants to steal this electron from silicon. So now we call this type of structure, this type of semiconductor, a p-type semiconductor. P for positive. So for N-type, we have introduced 5 valence electrons. For P-type, we introduce an impurity of a certain atom with 3 valence electrons. So now for the energy bands of this P-type semiconductor, this is our conduction band, this is the valence band, there will be another energy band introduced here because of the hole. So this P-type semiconductor means that uh, uh, so this act of stealing electrons from the neighboring atoms gives, for example, this electron is actually taken away from silicon. So now it is located here inside the gallium atom. Notice that gallium has a lower nuclear charge. Okay. Gallium has a lower nuclear charge than germanium. So if that is the case, if an electron is bound to gallium, it will require less energy, so that what happens is it will move up this energy band. So instead of not having this band, because all electrons in the germanium atom are bounded inside its atom, this new electron, this stolen electron, will introduce another energy band because it requires less energy to move it to the conduction band. So these two types of semiconductors, P-type and N-type, or P-type can also be called acceptors, N-type as donors. These two types of semiconductors will be used to will be combined, such as PN will be combined to produce certain electrical materials with fascinating properties, and we in the next lesson we will talk about their combination. So we'll talk about the PN junction.